Hello, Glenn class. This is Travis Bledsoe coming with another lecture video for gear drives. So I'll post the presentation on the D2L website if you want to look through the presentation. Also has the links embedded in that. There's some video links that I want you to watch. One right now before getting into this, and another one toward the end of the presentation. So I put the links in the comment section below. As I've tried before, my computer's not fast enough to keep up with the videos playing as recording this video and playing another video from YouTube. So if you can watch that independently, it would be great. And if you want to pause now to watch the intro for how gears are made video, and come back and pick up on where we left off here. So continue on. The gear drives provide a non-slip means to transmit power between two shafts. They change the speed of shafts, so you can change the different sizes of gears and get different speed outputs. And they can also change the direction of the rotation of the shaft. And those are called idler gears. And we'll look at those coming up. So here on the left side, you got a picture of gear drive. This is your basic economical spur gear setup. So looking on the right side of the little diagram, there's a few things. It's kind of a busy diagram, but there's only a few things I want to point out. So there's two different or two major types of gears that have different teeth angles. Okay, there's a 14.5 and a 22-degree angle, and it comes from that pressure angle right here. It's a kind of a ratio between a cross section with the baseline of the gear and a 90-degree mark through the pitch circle. So you have to pick out gears that have the same pressure angle. They will not interchange. We'll look at that in a couple slides ahead. Another thing is your pitch circle. If I can find the mouse here, pitch circle is right there, and that's about in the middle of the tooth. So that's right where the teeth engage. Notice the teeth are not meshed together of your gear all the way to the bottom. You've got a gap right here, so you want to have some gap. There's a gap at the bottom. Keep losing that mouse. Gap at the bottom on the back side. So you want a little bit of play inside that gear. You don't want to mesh tight. That's called backlash. And we'll look at that when we get in the lab. We're creating some backlash in the gear. So how to measure that. And then the pitch circle, it's not listed on here, but pitch circle, if you go all the way across here, we've got the pitch circle on this side. So that would be your pitch diameter of a gear. And you need that to figure out your center to center distance. It's not necessarily taking the outer diameter of your gear and doing the math on it. You need your pitch circle to find out center to center distance. We're going to look at the next slide. All right, some gear terminology. So gear ratio. The best way I can describe that in this video using words is how many times your smaller gear will have to turn in relation to your larger gear. So let's go back to the previous slide and talk about that. So I've not counted the number of teeth on these gears. I have no idea. I'm just going to throw out some numbers. So this smaller gear on top, we'll say it has 25 teeth. And just for easy math, we're going to do the bigger gear has 50 teeth. So what we're going to do is divide the number of teeth on your smaller gear into the number of teeth in your larger gear. So our smaller gear is 25 and our larger gear is 50, and that's going to be a division of 2. So we're going to express that as 2 to 1. So let's go back and look at that. So if the smaller gear is 25 teeth, it's going to have to make 2 full rotations for 1 rotation of the larger gear, which has 50 teeth. So that's our gear ratio. It's 2 to 1. And if that doesn't make sense, let's back up a little bit and go a little bit simpler. If you have a gear that is 25 teeth and you have another gear that's has 25 teeth. You have those meshed together. So 25 divided into 25 is 1. It's a 1-to-1 ratio. So you have, the one gear has to turn one full revolution, and the other gear turns one full revolution. So that's a 1-to-1 ratio. In the case of it's 25 to 50, that's a 2-to-1 ratio. And I guess you can get the point. Moving on up, you get different ratios of gears. You can your smaller gears will have to make more rotations as the larger gear gets bigger. So pitch diameter, I talked about that a little bit, is determined by the teeth, the point where the teeth make contact, where the force is applied. Diametrical pitch, that's another measurement you need on your determining the gears. And just kind of look at that last sentence in that paragraph. Diametrical pitch is the ratio of the number of teeth to the pitch diameter. So you can count your number of teeth that's on the gear, and then divide the pitch diameter into that. And that's going to get your diametrical pitch. Pressure angle, I talked about that in the previous slide. Your standard angles are 14.5 and 20 degrees. Those cannot be interchanged. Think about our thread systems that we had in a couple classes back. You got fine threads and coarse threads. They do not interchange. So you've got to have the same thread makeup. So in this case, you got to have the same angle makeup on your gears. So your center distance, and I talked about your pitch diameter, that you need to know that. So you take your pitch diameter of gear 1 and your pitch diameter of gear 2, add those together, and then divide that by 2. Go back to the previous slide so you can look at how they come together right here. Is your pitch diameter. So that's essentially the measurement that you're inputting in. You're adding the pitch diameter of both the larger and smaller gears, and you're dividing that by 2, and it gives you your center to center distance. So some basic types of gears that we'll talk about: spur gears, helical gears, bevel gears, worm gears. Spur gears is the most cheapest. They're economical. They're low to moderate speed applications. They're widely used across the industry. Helical gears, these are similar to the spur gears, but the teeth are at an angle. So this makes the teeth wider. Since it's cut in an angle, the teeth are wider, and so therefore they're stronger than spur gears. So they're cut in an angle, stronger than spur gears, and they can run at higher speeds than spur gears. What's unique about the helical gears is they have a right hand and left hand angles. The next slide shows that a little bit better, but you can see it on this slide as well. Down the bottom right, that picture of 2 gears. Notice how the teeth are angled. The one on the picture on the right, the gear on the left has the angle of the teeth going to the left, and the one on the right has teeth angled to the right. So that's the 2 angles. And to get your shafts running parallel, as you can see from this gear and this gear, if you had shafts in that, they'd be parallel. So to have your gears parallel, you'd have to have opposite angle or opposite hand angled gears, a left and a right meshed together. If you took a left hand and a left hand, or a right hand and a right hand, you can only get an application to where your shafts are running perpendicular. So this shaft would be, in our case, going upwards, and this one would be coming back toward us. So this slide shows that a little bit better. The 2 gears on top, you've got here's how the gears are leaning to the left, and then on the right side on top, you've got the teeth are leaning to the right. And as those pictures are together, you can actually mesh those teeth of those right hand and left hand angles together in that orientation and have your shafts running parallel. So to get shafts that are, maybe cutting you off here at the bottom. I'm going to try to change the view where you might be able to see it a little bit better. Okay, maybe you can see that maybe. So at the bottom, you got two left-hand helical gears, so your teeth, I'm sorry, your shafts running perpendicular, and two right-hand angles, your shafts are still running perpendicular. You have to take a left hand and a right hand to get your shafts running parallel. So helical gears, what's pictured here, you've got a double helical and a herringbone gear. So if you've got a double helical, is going to have a groove in the middle, like the one on the right side, or the picture, the real one there on the left side. Notice that they've got a left hand and a right hand angle. So think about, what's the purpose of that? So we talked about having a single right hand and left hand helical gear. Go back to a previous slide. The disadvantage of using these are they create axial thrust load. So when those gears are meshed together, they're creating a thrust load down the shaft. Anything attached to that shaft is experiencing that thrust load, like your bearings. Using a helical gear, or the herringbone gear and double crossed helical gear, you're going to have a left hand and a right hand on the same shaft, and what that's going to do is counteract each other. It's going to balance out, so there'll be no axial thrust load. These eliminate that. Your herringbone gear is in the middle, and it's basically doesn't have a groove down the middle. You've got your V connecting between your right and your left. So bevel gears, these are always going to be applications where your shafts meet at 90 degrees. They're going to be perpendicular to each other. You can't use bevel gears and have your shafts running parallel. So basically, these are changing the direction. If you've got your motor mounted in one orientation and your equipment mounted in a different orientation, you can use these bevel gears to change the direction of that shaft. So the teeth can be straight, like on the picture on the left. You got straight teeth on that. And then on the right, the teeth are cut in an angle. They're spiraled, they call. So you can have different ratios of these, but if you have two miter gears, two bevel gears that are have the same number of teeth, these are considered miter gears. And the only advantage of this is changing the direction of your shaft. Instead of being going vertical, you can now change it to horizontal, and you're going to maintain the same speed and output at the end. And the picture on the left, you're going to have a difference in speed because you have two different gears sizes. Worm gears, these are unique because they've got like a threaded cylinder that's called the worm, and it has made it into a gear that looks similar to maybe a helical gear, but the way it's made in the middle, you probably can't tell in this picture, but the round gear on the bottom, actually in the teeth, it's kind of dipped out to accept the spiral shape of the worm. So these consist of worm and a worm gear, and they're mounted on shafts, two shafts at right angles. These are always going to be right angled gears as well. They won't be parallel shafts. The unique thing about these are the drives are considered self-locking. So the driver in these applications is always the worm, the spiral gear that's on top. They're a high torque application. So the driver is always the worm, and then the one on the bottom is the worm gear, and it is always the driven. The driven one, the worm gear, cannot turn the worm or the spiral cylinder, threaded cylinder. So it's considered a self-locking gear. We'll talk a little bit about idler gears. These are used to change the direction of rotation. So we've got two shafts that are running parallel. So in this picture, we've got three different setups. The driver gear is on the right of all three of the setups. Driver gear is all the same size in this particular picture. Notice the setup on top. We've got a driver gear that's going counterclockwise, meshed in with another gear, and that other gear is turning clockwise. So you've got counterclockwise input and output of your driven gear is going clockwise. So what if you needed your driver, your motor is turning counterclockwise, and then you needed your output shaft to also be counterclockwise? You put an idler gear in between them. So the idler gear takes the clockwise motion, and then it converts it over to the counterclockwise direction. So here we've got counterclockwise meshed in with the idler gear that's going clockwise, meshed into another gear, making it go counterclockwise. So your output gear is going in the same direction as your input gear. Now this is to show illustration. There's no logical application to ever mesh two idler gears together. In fact, that's kind of going against, I guess, I don't know, the laws of engineering, but you're creating more friction. The fewer gears that you can have in a setup or a system, the better off you're going to be, because you're going to have less friction build up in that system. So here we've got just for explanation or demonstration, we've got counterclockwise input going to idler gear, it's going clockwise. It's going to an idler gear, it's going counterclockwise. And then it's meshed into a gear that is now going counterclockwise. I'm sorry, going clockwise. I'm getting all that mixed up going through them, but there's really no point of having a setup with two idler gears. So you can buy pre-made from the manufacturer or distributor gearboxes or speed reducers. These are going to be setups that have a certain input speed and an output speed. So they're going to have a ratio tied to the gearbox and a max speed and max torque and all that. So you can buy these boxes pre-made to where you don't have to create your own and mount the bearings and all that. These have got the bearings already mounted inside the housing. And there's different orientations of these and for different applications. There's the one on the left, you've got the input coming straight in and your output is going straight out that way. So on this one on the right, you've got an input coming in actually from the worm gear on top, and you're changing direction of the shaft. So it's coming out the side now. So you're going 90 degrees on your shaft direction. These can come in different size gears and ratios, so you're going to have your torque multiplication depending on the size of ratio that you have. Here just shows a couple pictures of some gearboxes. The one on the right would be one that you mount straight to a motor face. I think the motor face for those is a C-mounted motor where they mount directly to a gearbox. So you'd have 4 bolts on the front of your motor. Your shaft of your motor will go into the input shaft of the gearbox, and then your 4 bolts are going to bolt into the flanges of the gearbox. Then on the picture on the right would be this input will still be on the top shaft closest to us in this picture, but we would need a coupling to connect your motor and your gearbox. So here's another video that I want you to watch. I'm going to put the link down in the bottom. I want you to take time to watch this video. It's a really good demonstration of your gear ratios and torque multipliers, and adding in the gear train, multiple gears, more than 2. So this is what internal of a manual transmission looks like. This is I have another video link below that you can watch. It's optional if you want to watch this one, if you want to understand how a gearbox, I'm sorry, a transmission actually works when you're changing gears. Um, the video goes through basically using the picture there on the bottom of when you change the gears, what's happening inside of the transmission to get your different gear ratios. So if you get any questions, feel free to email. When you watch the video, please send me an email about that as well to let me know you watched it. And got questions, put them in the email. And if not, we'll meet in lab and follow up on any questions that you may have about gears. Take care.